Okay, so this video we're going to go over the two main types of circuits. We've kind of touched on them briefly before, but now we're going to give them names. Series and parallel circuits. Okay, so there's two different types of circuits. You've seen pictures for these before. Series, the resistors are in one continual loop with a power source. Parallel, there are branches. So again, for series, one loop. They all get the current. It's all one big continuous string. You take one off, the circuit is incomplete. Parallel, you have these branches. So if you take off one, there's still a path for the current to go through. So figure 2311 shows two identical light bulbs connected in series. Which bulb's brighter, A or B, or are they equally bright? Take a moment to guess. If they're identical bulbs, okay, they're identical bulbs. We know that they're in series, so they're going to carry all the same current through them. So because they carry the same current, power, we learned that power dissipated by a resistor is power is equal to current squared times resistance. So if the two bulbs are identical and have the same current passing through them, the power dissipated by each bulb is the same, which means that the brightness of each bulb is the same. So that means the voltage across each light bulb will be the same as well. So they carry the same current, they have the same brightness. Now if you think about back to our previous video here, since the voltages across each are the same, each of these are going to be half of the total the voltage across the battery. Okay. So you might be thinking that A is going to be brighter because it uses up more energy. Not really. Okay. So if one bulb can't carry the current, the other one's not going to get it either. So it doesn't. If you take out B, it's not like A is going to be lit up because there still needs to be a complete path. Okay, so we have two resistors connected in series. So there's no junctions. The current I must again is the same for each resistor. Talk again about the potential difference decreasing across these. But adding up the potential differences, they're going to be the same as the total EMF of the battery. Again, so the EMF voltage plus the difference in voltage between these two are going to be equal to 0. All right. So in this case, voltage drop across the two resistors in the direction of the current are delta V1 equals current times the resistance of resistor 1, and delta V2 equals current times resistance of resistor 2. So we can solve the current. We know that the EMF is the change in potential differences across each two, which is equal to the current of resistor 1 plus the current of times resistance 2. The current is the same. So we can say the current is the voltage, the EMF, divided by the sum of the resistance of each of those two, because they are in series in the circuit. So if we place two resistors with a single resistor, we have what's called the equivalent resistance. So you just add these two up, and when they're in series, the resistances just add up. And that gets what the resistance would be in one resistor if we didn't have the two, if we combine them into one. So for series, to get the equivalent resistance, you just add them together. So the current in a single resistor circuit is this. The single resistor is the equivalent of two series of resistors. So if you have a bunch of series resistors, you can add them up, and your equivalent resistance is the sum of those. So the equivalent resistance of resistors in series is just the sum of each resistance of resistors. And then you take the voltage of the battery, the potential difference on the battery, divided by the resistance, that's the equivalent resistance of the circuit, and you can get the current that flows through each of those items. So hopefully you can see, if the potential difference remains constant, and you keep adding a bunch of resistors, this is going to get bigger. your current is going to get smaller. They are inversely related to each other. All right, so we have a string of Christmas holiday lights that are 50 bulbs wired in series. What's the potential difference across each bulb when the string is plugged into a 120-volt outlet? So there are 50 bulbs in series. They're all the same. And the current in each of the bulbs is the same because they are in series. They're all getting the same current. They're all getting all the current passing through the circuit. So again, we apply Kirchhoff's law. We find that the potential difference across each of those, the sum of each of those potential differences, is equal to the potential difference of the power source. In this case, the bulbs are identical, and because the current of the bulbs is the same, all the bulbs have the same potential difference. The potential difference across each bulb is really 1/50th of the power source. So 120 volts, which is the potential difference across an outlet, divided by 50, means that each light bulb has a potential difference across it of 2.4 volts. Okay, so 2.5 volts, because the potential difference is shared by the light bulbs, so it's going to be really small. Okay, so when we compare two circuits, one with one bulb, one with multiple, all the batteries and bulbs are identical. How does the brightness of the bulbs in the different circuits compare? So in the circuit with one bulb, circuit A, the battery drives the current. Circuit with two bulbs with the same resistance, the equivalent resistance is twice as much. So the current running through the circuit in circuit B, the 2 bulb, is voltage divided by 2 times resistance. So since the EMF from the battery and the resistors are the same in each circuit, the current in B is 1/2 as much as A. So that means that the bulbs in circuit B, because they're getting half the current of that in A, are going to be half as bright. So this is a big thing here. The battery is a source of potential difference, not the source of the current. So the battery doesn't provide the current in the circuit, but the amount of current depends on the resistance. The amount of current depends jointly on the battery's EMF and the resistance of the circuit attached to the battery. So the battery provides kind of a push, not the movement of charge. It provides that push to make it move. But and it'll be hampered by the resistance of the elements of the circuit. Okay, so parallel circuits have bulbs that are connected at both ends. They're connected so that their bulbs are connected in different loops. So which bulb in the circuit is brighter, A or B, or are they equal again? So hopefully you can see that there's the voltage, the potential difference, or the electric potential at these points are the same because they're still coming from the battery. Okay. And the potential differences across the bulbs are equal because the light bulbs are the same. The potential at these 2 points are the same as well. And because these bulbs are the same, because they have the same potential differences, they're going to have the same current moving through them. And they're equally bright. But the trick is with this, current is determined by the potential difference, and since they're connected in parallel, they have the same potential differences. Not only do they have the same potential differences, but they're the same as the power source. Now, we talked about resistors and equivalent resistors in series. When you look at equivalent resistors in parallel, they're different. So again, when we look at the potential differences across each resistor in parallel is equal to the potential difference of the battery because both resistors are connected directly to the battery. They each have their own individual loop. They're not sharing potential difference with anybody else. They get their own individual loop. Okay. Now we get these equivalent resistance pieces. So according to the junction law, the current gets split between these two. So the current coming out of the battery is split between resistor 1 and resistor 2. So we have a sum of current. And current is voltage divided by resistance. So current is equal to the current of 1, delta V1 over R1, plus the current of 2, delta V2 over R2, which is, in this case, since we know that each of these have a loop to the power source, the potential difference is the EMF, the voltage of the battery, divided by the resistance of 1, plus the potential difference divided by the resistance of 2. So we can say we can factor out the voltage of the battery, and we can say that the current of the battery is the potential difference of the battery times 1 over the resistance of the first one plus 1 over resistance of the second one. That's a big difference from the series circuit where you just add them up, the resistances. Okay, so can we replace a group of parallel resistors with a single equivalent resistor? Yes, you can. Okay. To be equivalent, delta V must equal the EMF, and I must equal the current of the battery. So we have these two. So delta V over I equals EMF over I. Now, if we flip this back to here, I is equal to all of these. So this is the equivalent resistance. So equivalent resistance we can do for parallel. But now we're going to use a little different formula. We're using this. So in series, to find the total resistance, the total equivalent resistance, you add them up. Just straight add them up. In parallel, what you have to do is 1 over each resistor. So 1 over resistor 1 plus 1 over resistance 2 per how many will you have over that? And then do 1 over that. Because really it's 1 over equivalent resistance equals the sum of these. Okay. So it's going to get the resistance gets really small the more resistors you add. So 1 over equivalent resistance equals 1 over the resistor 1 plus 1 over resistance 2, blah, 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 all the way to the end. Okay, so if we look at each bulb in these, now we have a parallel circuit. They have the same potential differences, but now we have to figure out the equivalent resistance of these. Okay. Each bulb is connected to the same potential difference out of the battery, so they have the same brightness. And in the second circuit, the battery must power 2 light bulbs, so it provides twice as much current. But these all A, B, and C are going to have the same brightnesses because they all are on one loop between them and the battery. Okay, so now what we're going to do is you have these 3 resistors. They're connected to this 12-volt battery in parallel. We're going to figure out the current provided by the battery for this circuit. So we can reduce them to a single equivalent resistance, so we've got to do that first. So to do that, so the equivalent resistance is 1, since they're 58, 70, and 42, we're going to do 1 over 58 plus 1 over 70 plus 1 over 42, and then take the 1 over that. You can't just flip it upside down. That doesn't get you the right answer. So it's 1/58th plus 1/70th plus 1/42nd, and then take 1 over that. And we get our equivalent resistance to be about 18 ohms. So current, because current is EMF, the voltage divided by resistance, our potential difference here is 12 volts. That's coming out of our battery, divided by our resistance of 18.1 ohms. Which means that the total current moving through this system is 0.66 amps of current. So 1 over 58 plus 1 over 70 plus 1 over 42, take 1 divided by that gets us our resistance, our equivalent resistance. Voltage divided by equivalent resistance gets our current. So that means that coming into the branches and going out of the branches, it's 0.66 amps of current. Okay. The equivalent resistance of this is a lot less than if we had these in series. If you think if we had these in series, that's a lot, 170 something ohms of resistance if they just had them in series. which means that if you have an equivalent resistance, it drops the resistance, which means you'll have more current in there. All right, so parallel resistors, so more resistors would imply more resistance. In series, yes, but in parallel, no. Hopefully you can see that from the math. So the parallel resistors provide more pathways for the charge to get through. So the equivalent of several resistors in parallel is always less than single resistors in a group. This is big. Okay, resistors in parallel always have less equivalent resistance than those in series. And they have the driving analogy here too. If there's an alternate route for cars to travel, more cars will be able to flow because they'll have multiple ways to get through places. Okay. Okay, so we're going to look for the current supplied by the battery in each of these. Okay, so we have 3 15-ohm resistors and a 5-volt battery. So the equivalent resistance is, since they're each the same, 1 over 15 plus 1 over 15 plus 1 over 15. Take an inverse of that, so 1 over 1 to the 5th, which is 5 ohms. So the current is voltage divided by resistance. Voltage is 5 volts. Resistance is 5 ohms. The current is an amp. So we have resistors connected in to a power supply works at a heater. Which of the following circuits will provide more power? So again, we're going to have to figure out the equivalent resistances here. I'm going to give you a hint on this one. If you have 2 resistors that are in parallel that are the same resistances, your equivalent resistance is half. So if you look here, this one, the parallel circuit, the equivalent resistance would be 9. The equivalent resistance for series is 36. See, told you. So the circuit on the left has an equivalent resistance of 6 ohms. The power is voltage V squared divided by R. So 81 over 36. For the parallel circuit, the equivalent resistance is 9. So the power is 81 divided by 9. Okay. So you have greater power on the right. When you have lower resistance, lower equivalent resistance, you'll have more power. All right, that's the end of this video. There's a lot of stuff on this one. Make sure you look at the series and parallel circuit information and answer the questions on the Google video, and we'll talk to you soon.